Well, hello guys and welcome back to Mr. G Physics. Here Mr. G, and this time we're going to be doing an experiment for the grade 11. This is the formal experiment for term 1 and it's going to be to study the relationship between force and acceleration. This one is related to Newton's second law of motion. I have here all the materials we need for the experiment. Starting with the ticket timer, we need the ticket timer to measure certain things there. We need obviously two conducting wires so we can connect to the ticket timer. We need the batteries. In this case I have 4 batteries, which when I connect them together I will have a potential difference of 6 volts for the ticket timer to work. We have the track, we have a trolley, and this trolley is attached, it's a thread which I use. There is a thread. This thread is attached to a hook that is going to move through the pulley. I just show you in a minute. We have some mass pieces, we have the ticker tape, we have my coffee, we have some books which we are going to use through the experiment. So the first thing we have to do here is to set up the apparatus. But before we do that, we must make sure that the ticker timer is working properly. Now this ticker timer on this side have 2 buttons. These buttons are one of them to change the frequency between 25 and 40 Hz, and the other one is just to switch on and off the ticket timer. So the first thing we're going to do is to make sure that this ticket timer is working properly. So we connect here the positive with the red cable, the negative with the black conducting wire. We connect negative to negative, negative to negative, positive to positive, and we do a test for the ticket timer with 40 Hz. And it's connected. So the ticket timer is working properly. So all we're going to do now is to set up the experiment. For this, the track will have a place here that we can use for the ticket timer on this end here. So in that end, we can connect the ticket timer. There is our ticket timer connected to the track. Okay? Now we're going to make sure the trolley is moving through the track. Let's make sure the trolley is moving through the track. There we can see trolley moving through the track. We can always reduce friction by oiling the tires of the trolley. That will be ideal, guys. It will be amazing if you could do that, but I'm not going to do it right now. Later on we'll speak about that one throughout the experiment. So now here we are going to have the trolley that is moving through the track. We are going to have our thread. This thread is connected to a hook at the front here, and I have mass pieces that I can change. They are going to be attached to the end of the hook here. This is going to be moving all the time, all the way through the pulley, and then the mass of this, or the weight to the mass pieces, is the force that is going to pull this trolley. So if we want to change the force, we add masses at the end of the hook. And guys, this is more or less the experiment. This is what is going to happen. We're going to do it just now. Let me just attach this one, and then finally we need our ticker tape. So we are going to measure a piece of the ticker tape, which is the length of the trolley, more or less, and then we're going to repeat this one 3 times. I have already one. I already took another piece, so I have 2 pieces, and we're going to repeat this 3 times. Let me look at my computer. 3 times. So we need 3 of these pieces of ticker tape, more or less the length of the track, but we are not going to use the whole ticker tape. You'll see that we don't need the whole ticker tape. And guys, this is the first part of the experiment, when we set up when we have all the materials and we see that everything is working properly. Well, now that we have all the apparatus and we have the ticket timer operational and working, what we're going to do is to make sure we compensate for friction, because there is friction in the track. There is friction in the track, and as you incline this specific trolley, there will also be the component of the gravitational force that act on the trolley. So to compensate for friction, what we are going to do is to use some books. That's why I have some books, and we're going to incline the track a little bit so that the trolley moves at constant velocity when we place it on the track. So we leave the trolley on the track and we make sure the trolley is moving at uniform velocity. We're going to place all the mass pieces also on top. All the mass pieces we're going to use it is on top. So the total mass of the system remains constant. So we keep a small push and we see this trolley is moving more or less at constant velocity. We're repeating from the beginning. There we go. We give a small push to break inertia. It's moving, it's not accelerating. This trolley is more or less moving at constant velocity. You will never make it move exactly at constant velocity, but you get the idea that it's more or less constant. So friction is compensated here. If you incline it too much, it will accelerate. Let's do that so you can see it. Will accelerate and then it won't work because it means the friction is not compensated. The component of the gravitational force down the incline, or the parallel component of the gravitational force, is greater than the frictional force. We will see here it's moving faster and faster, and therefore it is accelerating. There is increasing towards the end. So we're going to remove this book, we leave it like this, and then the trolley is going to be moving at constant velocity. Remember, we keep all those masses there because that will make the total mass of the whole system constant. There you can see that it's moving at constant velocity. Let's place this thing back here. There we go. So we're ready then for the first reading. The first reading, guys, let me look here. The experiment you're supposed to do. The first reading is going to be with a 20 grams. So all we're going to do is to have the hook here. Let me take all these mass pieces. There we go. And here at the end of the hook, we're going to place 2 mass pieces of 20 grams. Okay? So that's all we're going to do. We're going to place it here like this, 20 grams. All the rest of the masses are going to place it on top of the trolley. So we keep the mass of the system constant. Okay? So now we're ready for the first run. Let's make sure the ticker timer is connected now. Positive side, I'm going to do it on this side here. Positive side. Negative side. Once more, switch it on. Ticker timer is working properly. So we're going to take here, we're going to attach one of the tapes we took previously, one of the tapes, we're going to attach to the end of the trolley. So we're going to pass it to this point here. We have the ticker tape there. Make sure the ticker tape doesn't increase friction. So we move it here. There is enough there. And then we are ready for the first run. We are ready for the first run. We switch on the ticket timer to the side here. There we go. And that was our first run. Beautiful. I can see all the dots beautifully there. Okay? So this is the first run, guys, and we are going to repeat now 2 more times. The second time we are going to transfer 2 mass pieces from here on top of the trolley. I'm trying to keep constant the mass of the system. So 2 mass pieces from the trolley I'm going to transfer to the hook at the front here. And we can see we transfer 1 and 2. Now the mass that is going to be acting on this string is going to be 40 grams because I transfer 2. So you can fit 40 grams here. 20 is 40. Then I attach now. I need to attach the second thicker tape. We got the second reading. So all we have to do is to repeat once more, and this time the first one is there, second one, and the third one we're going to transfer all the mass pieces to the front of the hook. There we go. So now it's going to be 60 grams. Now it's 60 grams. And this is the experiment. So we're going to get the last piece of thicker tape, guys. And guys, this is the experiment. We have our 3 ticker tape. We just have to now work with the ticker tape. But this is the part of the experimental part. I hope it helped. I hope you understand how we do it, and most important, why we compensate friction. But I'll see you just now. We're going to start working with the ticker tape, which is the most difficult part. This one is actually fun. Well, now that we are done with the experimental part, with the practical part, we can come here and start answering some important questions. We have to tabulate, we have to draw a graph, and we have to get a conclusion. Alright, so here is the part when we set up the experiment. Now we have to tabulate, and we are going to explain how to do all that. Now, first of all, we need to find the period of the ticker time, because the period, remember, is going to be the time between any 2 points. So period is equal to 1 divided by frequency, and now this one depends which frequency you use. So it's 1 divided by frequency. The frequency we use was 40 Hertz, so it's 1 divided by 40, and this is going to be equal to 0,025 seconds. So this one is the time between any 2 dots. However, we're going to work not with 2 dots, but rather with 10 dots. So therefore, we need to know now what will be the time between 10 consecutive dots. And how we do that? We just multiply the number of dots we want, which in this case is 10, but be careful. At school, maybe you do it with 5 or you do it with 20, I don't know. So it could be different number of dots. We are going to work with 10 dots, and you multiply 10 by the period, and that will give you the time between 10 consecutive dots. In this case, it's going to be equal to 0,25 seconds. That is the time. Now we have to complete this table with the data we got. We have 3 trials. Remember, we did 3 runs, and then in each run what we did was changing the mass of the mass pieces at the front, and therefore that will change the resultant force. So for the first run we did use 40 grams. So let's write here 40 grams, but remember, you cannot work in grams. So this was it was 20 grams. 20 grams for the first run, 40 grams for the second run, and 60 grams for the third run. That was the runs that we did, that is the mass that we used. And then when you convert, for the first one will be 0,02, 0,04, and 0,06, and this is in kilograms. So that is important to know here, guys, because now we are going to calculate the resultant force. Let's analyze what forces are acting on this specific system. On the mass pieces, this one is the mass pieces, okay? These mass pieces, you have weight pointing down and you have tension pointing up. Those are the 2 forces acting on that specific mass pieces there. On the trolley, you will have tension, this tension, which is in actual fact the same as the other tension on the mass pieces. We have weight straight down, this one is weight, there is friction pointing in the opposite direction of motion, that is friction, and there is normal force perpendicular to the surface, that is normal force there. So those are the forces acting on that trolley. But let's draw a free body diagram. Notice and remember that there is an incline here. There is an incline on that point. Let me just do it in a better way so you can see it. There is an incline, you can see it. There is a theta there. Okay, so now we are going to draw the free body diagram for the trolley. Okay, what forces are acting there? And for this one, I think maybe we should draw the axis so it gets better and easier to understand. This one is the x-axis, perpendicular to the x. You must have the y-axis, and then what forces are acting there. Okay, so we have normal, which is perpendicular to the surface. We may not use normal at all, but it's there. We have friction. This is frictional force in the opposite direction of motion. Remember, friction and normal 90 degrees because one is right on the y-axis while the other one is on the x-axis. We have the applied force, not applied force, but the tension. We have the tension. We have the tension here. And know the following: this tension is going to cancel with the other tension. So in actual fact, the force that is going to be acting here will be the weight of the mass pieces. And we also have the weight on the trolley, which is straight down, as I can show you here. This one is the weight on the trolley, straight down. This weight on the trolley have two components. It will have here the, let me maybe try to do it beta drone. There we go. Here we have weight in x. This one is weight in x, and we have here weight in y, which we are not going to work with it, but you need to know that we have weight in x and we have weight in y. Now let's work in the x-axis real fast, and we can work here in x-axis. All right, so F net is equal to tension plus weight in x minus frictional force, if we take the direction of motion as positive. So that direction there is going to be a positive direction. Now, because we compensate for friction, when we compensate for friction, there were no tension, and we keep that angle. It means that the weight in x will be equal to the frictional force, just in opposite direction, and therefore tension, weight in x and frictional force will cancel each other, and the net force will be the tension, which in actual fact will be equal to the weight in this specific object. So actually this weight here is the force that is going to be acting on the trolley. So I hope you understand, because this is the part that we have to understand to know why we have to calculate that resultant force and which one is the actual resultant force. So for this resultant force, we are going to use the mass pieces, because that is the one that we're looking for. That is the force that is being changing and is acting on that specific trolley. Friction was compensated. Remember, that was quite important. Okay, so we're going to calculate the resultant force in each case, which in actual fact is the gravitational force, but this one is for the mass pieces. So let's calculate each of them. For run 1, we have that Fg is equal to mg. The mass that we use was 20 grams, so it is 0,02 multiplied by 9,8, and this will be equal to 0,196 Newton. This is for the first run, and that number must be here, 0,196 Newton. Okay, for the second run, there we go. And then for run 3, so we write them here, 0,392, and then for the final one is 0,588 Newton. There we go, that part already. Now is going to be, I think, the most difficult part to understand. However, it's not that bad. We're going to work with the tapes. So we're going to work with the first tape for the first run, and then it's a repetition of each of them. Okay, so we are going to analyze this first run. Remember, run 1 was when we were with 20 gram mass pieces. So what we're going to do is we're going to count 10 dots or every 10 dots. I just darkened it a little bit because it was a little bit too light. So you are going to mark the first dot. You are going to look for this very first dot there, it's a little bit more to the left, that dot, the first one, and you are going to call that specific point there. It's difficult. There we go. That point is going to be point P. Okay, that is the starting point. That is point P, starting point. Now we are going to count 10 consecutive points. So let's enlarge so you can see, and we count starting from that. That one will be point number 0. We'll count
1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is my point number 10, and is going to be Q. Alright, I'm going to call that one Q. Then I'm count another 10. So it will be a 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This one is my 10th dot after Q, and I'm going to call that one R. Remember, you start from point 0. Okay, so you have actually 11 points, you have 10 spaces in actual fact. Okay, so we're going to count 5 now. The first 5, so it will be 0, 1, 2, 3, 4, and 5, and we're going to call that point there. Let me see if can I do it so you can see it nice. We're going to call that point there X. That one is X. 1, 2, 3, 4, and 5. So you count from Q another 5. So it's 1, 2, 3, 4, and 5, and we're going to call that point the Y. Alright, so I hope you understand this part here. So you should have something like this. You have PQ, you have QR, you have an X in between, you have a Y in between. 10 dots starting from 0. So now what we are going to do, we're going to take our ruler and we're going to measure the length of PQ, and we're going to measure the length between QR. That is what we are going to do next. Now for PQ, I got a length of 1,2 centimeters, which I'm going to convert to meters, and that will be 0,012 meters. Guys, this experiment is tricky. Now we're going to measure QR, and that gives me 2,8 centimeters, which when you convert it, you get 0,028 meters. So we have now the displacement. So with these numbers, we are going to calculate the average speed at X, and we are going to calculate the average speed at Y. How we do that? We use displacement divided by time. The displacement will be PQ because X is right in the center between P and Q. So this one is PQ, and the time was calculated before is the time for 10 dots. Okay, so I'm going to write here delta T still, and then we're going to substitute. So we have for PQ, we have 0,012 divided by the time, which is 0,25. So that gives me that the velocity at X is going to be equal to 0,048 meters per second. And we are going to repeat the same for Y. So we have now that specific data, which we are going to complete there in the table. So we can complete this table now here. Let me see the values we have. We have for the distance here was 0,012. For here was 0,028. And for the calculation of the velocity, we got 0,048 and 0,112. So with those values now we got 4 velocities. We have this and this value. We are going to calculate the acceleration. Okay, so we come in here and the acceleration is equal to a velocity at Y minus velocity at X divided by the time, which is the same because it's between 10 points. And now when we substitute here, we have that the 0,112 minus 0,048 divided by the time, which was 0,25. That will give me the acceleration for that specific point, and it gives me that the acceleration is 0,256 meters per second squared. So that is the acceleration. So the acceleration here is 0,256 meters per second squared. It's written already on top. Guys, we are going to repeat the same for run 2 and run 3. So we are going to repeat with the second run. All we have to do is to go to the very first point. Remember that point will be point number 0, and that point is going to be called a P. Alright, so we're going to start here and we count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is my point number 10, and therefore that one will be Q. I count from the 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and this one is my 10th point. It is going to be point number R. I'm going to take my ruler and I'm going to measure the lengths of those specific points. And then I got 4,1 centimeter for PQ and 8 centimeter for QR. Remember, you have to convert. So we already converted. So now we are going to count 5 points from P and 5 points from Q. So it will be 1, 2, 3, 4, and 5. If you count 1, 2, 3, 4, and 5, remember the first point is point number 0. This one will be my X. And from Q, 1, 2, 3, 4, and 5. And this one will be my Y. So we are going to calculate first of all the velocity at X. Remember, is equal to PQ divided by the time, and this one will be 0,041 divided by 0,25. That will give me that is equal to 0,164 meters per second, and we do the same with velocity or speed at Y. 0,32 meters per second. Now we have the velocity at X, or the speed at X and speed at Y. We can calculate the acceleration. Remember, it's the velocity at Y minus the velocity at X divided by the time, which is exactly the same. So when we substitute, we have that is 0,32 minus 0,164 divided by the time, which is equal to 0,25. So we get that the acceleration here is equal to 0,624 meters per second square. That is the acceleration here. And then the answers I got here, let's maybe fix that one, 0,624. We have the acceleration. Guys, all we have to do is to repeat for trial 3, which I'm not going to do. I'm just going to complete the table with the substitution here. And here we have all the reading. Now, we cannot analyze this table. It's difficult to analyze the table. So to analyze the result, we have to plot a graph. That is part of the experiment. We have to plot a graph so we can analyze the result. In the y-axis, we're going to represent the acceleration. In the x-axis, we are going to represent the resultant force. Alright, so now all we have to do is to plot the points in the graph, which could be also tricky. We need to know how much each of these small lines will represent when drawing the graph. So to do this one, all we're going to do is to divide 0,2 by the number of lines you have, which in this case is 5. When you do that, you get that each line will represent 0,04, and that is important to know. Okay, so the first point we have to plot is 0,196 and 0,256. That is for run 1. Alright, it means this one is the force, this one is the acceleration. So those are the first point we have to plot here. So we can be here and we do the same with the x-axis. We have that this 1 divided by 5, this one will give you 0,2. So this one will help us because we have to round off these points in order for us to be able to plot. So the force, we have only one side after the comma, so we have to convert. This one will be equal to 0,2, approximately 0,2, and this one will be 0, we can take 2 places after the comma, 0,26. So these are the points we are going to be plotting here in the graph. So we're starting with the x, which is 0,2, so that will be right in the first point here, so it will be right, that will be the 0,2. Now we're looking for 0,26, so if each of them represents 0,04, it means it will be between the second and the third point. So the first plotted point will be right there in that specific point. That is for the first run. For the second run, for force we have 0,392. We have to round off, remember, so we're going to round off to this is run 2, let's work organized. This one will be rounded off to 0,4, and for this one we have, for the acceleration, we have 0,624. We are going to round off to 0,62. There we go. So we're coming back here, we're looking for 0,4. that will be in the second point here. That will be the 0,4. It's a little bit too compressed, and then for the acceleration we have 0,62. So in other words, it's going to be somewhere there. That is going to be the second point. Then for run 3, and we get that the last point is 0,96 for the acceleration, 0,588, but we rounded off to 0,6. It will be in this specific point. If we go all the way there, will be, when you count, will be more or less here. Guys, if you look at this graph, is very accurate, which means it's almost a straight line. There is some reading problem, but not much. This graph is a little bit compressed. If you do it in the Excel sheet, I'll show you how this graph will look like. And if you draw the graph in Excel, which is much more accurate, this is what we get. We know it's a straight line, and therefore the acceleration is directly proportional to the net force. Guys, the rest of the experiment is just to do or write the analysis of the result. So what we have to say here, we have to say that the graph is a straight line, and therefore acceleration is directly proportional to F net. We saw it from the graph. We know that A divided by F net, if you calculate it, will get that is constant, and that is the mass is constant. All right, and then the conclusion, guys, is not other thing that the Newton's second law of motion for the part of acceleration versus net force. When the mass of an object is constant, the acceleration is directly proportional to the net force. Guys, this is the experiment. I hope it helped. It could be difficult. It could be difficult to do it. Here is all the calculations at the bottom. There is some question. I don't want to show you that question. There is all the calculation with all the measurements at the bottom, and then the graph. I hope it helped. If it helped, thumb up, subscribe for the channel so we can do more experiments. I'll see you next time. Mr. G here.